talk about the Advanced Forming Research Centre. What I really want to talk about is a little bit of background about the But also we have an office here in Sheffield, down in Attercliffe, so that we can engage with the forming and forging industries in South Yorkshire, Lincolnshire and the West Midlands. So just to give you a bit of a background on the AFRC, it was launched in 2009 with 12 staff with a capital investment from Scottish Enterprise of £20 million. There was a purpose-built phase 1 building of approximately 2,000 metres squared. Had a staff of 20. In 2011, we were one of the original members of the High Value Manufacturing Catapult, so like the AMRC, Warwick Manufacturing Group, and the like. We doubled in size in 2014, and we have, in terms of square area, and we have about 80 members of staff. Around 2017, also the Scottish Government gave us the opportunity to run the Lightweight Manufacturing Centre, and in 2018, the £56 million National Manufacturing Institute Scotland was announced by the Scottish Government, and Strathclyde University was the anchor university, and the AFRC was the original element of the National Manufacturing Institute of Scotland. In 2019, the Lightweight Manufacturing Catapult Centre opened up its own centre, split from the AFRC. And in 2020, we built another purpose-built area to start the housing of the so-called FutureForge, which I'll talk to you about in detail later on. We also then in 2021 opened up the Metallurgical Research Centre with Boeing, which is another building specifically related to manufacturing processes with a direct interaction with Boeing. And in 2022, when you come to Glasgow and arrive at the Glasgow airport, you'll see a very big purple building. And the National Manufacturing Institute of Scotland's purpose-built building, particularly focusing on digital technologies, is opened. Key important observation here, therefore, the AFRC has now returned back to its core business, which is forming and forging. So we have about 80 members of staff, delivery staff, I should say, that focus completely on forming and forging of metals. So we are the UK's national asset for industrial scale metals forming and forging research. But at the same time, we're in a very unique position from a catapult perspective. We have this distinct, deep capability in forming and forging, but we have access to all of NMIS's broader capability, such as in digital technologies and connectivity, in industrial 4.0 type capabilities, as well as lightweight manufacturing. So we're really a unique catapult centre in the sense that we have a core competency that no one else has, but at the same time has access to all the broad technologies that we modern day think about in terms of a catapult. So just to make that point, so the NMIS group, the National Manufacturing Institute of Scotland group, we have the specialist centres, the Advanced Forming Research Centre, the Lightweight Manufacturing Centre, but then inside the NMIS we have the Digital Factory, where all the digital skills, Industry 4.2 scenarios, we have a collaboration hub, but most interesting as well, we have a very large manufacturing skills academy where we're upskilling large numbers of engineers and technicians in Scotland, but also apprenticeship schemes and graduate apprenticeship schemes as well. So just in terms of our partners and our members, I'll just give you an indication of what type of membership we have. So these are our Tier 1 members. So you can see quite clearly we are an aerospace-focused research centre. We obviously have the OEMs, but also their supply chain. So it's really interesting, but it's very bespoke. All of those companies are very much focused on aerospace and aerospace supply chain in metal. And we also have a number of Tier 1 partners, as you notice, some local ones. So Sheffield Forge Masters has recently become a Tier 1 partner, as well as we have now a significant number of Tier 2 partners. And again, we've had a large number of Sheffield-based companies join recently in our quest to understand and engage with the broader supply chain. Initially, we're very much focused on the OEMs, but now we're very on a focus now on supporting the whole supply chain from very small companies such as Footprint Tools. Footprint Tools is, for example, a tier 2 member, all the way through to obviously much larger Sheffield-based companies. So what is our strategic plan? So our vision, apologies for this particularly small font, but our vision is to advance forging and forming to become more agile, more economical, more resource efficient, and better performing products using emerging digitalisation technologies. So our major drive is towards developing digital twins of forming and forging processes, as well as supporting the UK manufacturing base. And that's our purpose, to support the UK forging and forming industry and our international partners. I should point out to you that only one of our tier 1 partners actually has a head office in the United Kingdom. The rest of our tier 1 partners have head offices all over the world. So we are effectively an international research organisation. Our target partners are forging houses. So for example, that's why we've been very much active in the Sheffield region recently, gaining more traction with the local forging houses, forming users, equipment suppliers, and lower TRL producers. We're in a very fortunate position. We've become members of the Henry Royce Institute. So from a catapult perspective, we have direct access to lower level technology development, and we can put it straight into application. So in fact, we have a number of programs working with the Henry Royce Institute on and towards developing that into more industrialisation. Our objectives are to de-risk and accelerate innovation in forming, enable industry to develop and scale up the next generation of forging. Maybe from a local perspective, something that's really important for us is develop traditional technologies towards Industry 4.0. You know, there's lots and lots of discussion about all these fancy Industry 4.0 type of activities, but what we're really keen on is enabling companies in the local area, for example, to get low-cost digital solutions which actually add value to the company, not necessarily add significant levels of cost. And another important element, as you probably realise, we want to extend the AFRC remit beyond the aerospace sector, and hence we're often down here looking in automotive and nuclear sectors. And our strategic priorities are productivity improvement, digitalisation, sustainability, and most importantly, skills development. You know, the United Kingdom's forging and forming industry is dependent on only one really important element, and that is human resource and the skills that those human resources bring. So it's really about helping develop those skills to be fit for purpose for the 21st century. And our key project area is really about NMIS more than us, but it's net zero manufacturing, reduction of overheads, extend innovations into the supply chain, extend innovation to ancillary processes, and the digital transformation. This is a little bit of a busy slide, but what I want to just show to you is what the capability, what the structure of the AFRC is. So we have a NMIS CEO, Chris Courtney, he just started. Then there's myself as the director of the AFRC. We have head of operations, Alistair Conway, and we have 3 key teams: materials team, forming, and forging in Incremental. So the forging Incremental is very much focused on near-net shape forging processes as well as traditional type forging processes. With forming is very much focused on sheet type activities, and materials is in a broad range of activities based on material science and engineering, and with one key skill set, and that's residual stress. I'll give you an example of that later. We also have obviously a number of technical sports. So altogether, we have 80 delivery staff working on forming and forging of metals. So what's forging at the AFRC? Well, our facility was generated to support 2 key points: the fundamentals of deformation and materials evolution, and to link base research with production, demonstration, validation. So we have 3 types of hot and cold forging applications: bulk forging, such as standard open die or closed die forging, some precision forging, and near-net shape manufacturing, such as say shear forming or flow forming, or something like radial forging or elements like that. Industry adoption is very much across the sectors, very much dominated by aerospace, but we also have significant investment and engagement with the automotive, energy, and oil and gas sectors. Our key capabilities are in steel, nickel, not unsurprising considering that we're an aerospace-driven company, but we have now significant development work in steels, particularly on high-end, high-strength duplex stainless steels and the like. So here, just to give you an example of the size of the back room with some of the kit that we have. So, for example, here we have a screw press here, which effectively reflects the production facility in Inchinnan, Rolls-Royce, just across the road from us. It's a 2,100 ton press with a 1,200 degree rotary furnace. We have a very standard 500 ton hydraulic press. The interesting thing about the hydraulic press is that we've completely broken into it, and we've put all sensors on all of the activities and demonstrated that you can make a old press into Industry 4.0 ready. So this is a really important press for us, because effectively now we can collect any information from that press without interacting with the control system at all. But it still give us feedback and actually then control the control system with a high degree of confidence. We also have significant heating technology capabilities, large number of furnaces. We also have our current largest gas furnace is about 1 metre cubed, but I'll show you that we're actually going to have one much bigger than that in a second. The key point here is that we have industrial size equipment. Okay, it's all industrial size, so it's about proving out technologies at the right scale, such that we can de-risk the innovation cycle to our members and to our customers. So probably one of the most interesting aspects of the AFRC is our competency and capability in incremental forming of metals. So instead of doing bulk deformation, do localized deformation. So we have near net shape capabilities in flow, shear, and spin forming, rotary forging and radial forging. And this has been adopted in a number of sectors such as the automotive, aerospace, energy and oil and gas. And those are the types of materials that we've been able to do. The key interesting observation about this area here is that we've got all this, I've got a lot of capability, but there's a lot of hesitation in the UK manufacturing sector to invest in these areas, whereas other economic zones are investing in this area significantly. So a really interesting observation. We do a lot of interesting pre-competitive research in this area, but most of our competitive research is done in the bulk metal forming area, owing to the fact that the UK, it reflects the UK manufacturing heartland, mostly in bulk forging. However, all the innovation in many respects is being done here, and this is where significant environmental and cost savings can come if you could near net shape a component and take away a significant amount of machining and the like. Significant savings could be had. And environmental cost. So here's some examples of just near net shape forming applications. So we have flow forming on this side, where effectively we're extruding using rollers here over a mandrel, a hollow component that's literally stretching it out, making it into a long tube. So you can see in these cases they started off short and fat with a hollow tube, and they've been extended into complex shapes. That's all in one go. So something like that would only take about 10 to 15 minutes to do from a solid hollow cylinder, all at room temperature. Okay, so there are some technical issues to overcome in this respect, such as some significant levels of residual stress and the like. But it's amazing what types of metals can be formed using this approach. You wouldn't believe some materials with incredibly high tensile stresses can be formed this way, which wouldn't be able to conventionally formed any other way. And then obviously you've got the other side, you've got a shear forming process, where in this case we're making a relatively simple cone. But we've got examples where just from a solid plate, we can make a mag wheel within 3 or 4 minutes, just using this approach. So you can see the real complex shapes that you can generate using these types of applications. And most of these applications have been done in one pass, without the requirement of any heat treatment, intermediate heat treatment, or anything like that. So really, really exciting technologies that could really have a massive impact in terms of sustainability, but also cost reductions. In fact, this I think is a really interesting one. So this is our rotary forge here. Well, we used to be at the AFRC, now it's at IFA. So what we've decided to do, once we've proven out the technology, we don't want to keep it there anymore. We don't want to keep that. We want to make it an asset for production purposes. So in this case, we've made a collaboration with IFA. So IFA now have this. The market and obviously they've got a business case, but at the same time we can use it for research activities in the future. So I think this is how we're going to go in the future. We're not going to have large assets sweating for only 10 or 20% of their time. We're going to put them into industrial situations to then have access. We think that leads to actually a faster transition of technologies and leads to probably more companies actually taking on that technology once they see that one company can utilise that technology. And you can see, again, in this case, we some radial forge components. Again, these components were made up from one piece, which was a monoblock of some sort into some complex shapes. If you want, I can talk about these individual technologies. But the key observation here is that there are many, many near-net shape manufacturing processes that could be have a significant play in the next 10 to 20 years. So in terms of investment, these are some of the most interesting technologies if you can find a business case for them. We also have, and just going on to sheet metal forming, we have some very impressive superplasticity equipment, for example. So this is a 2,000-ton SPF press. So this is a really small one, 200 tons, sorry, just to prove out some technologies. But we also have a 1,200-ton superplasticity press and a creep forming press. So we've proven out creep forming up to 2 or 3 inches thick of titanium in making complex shapes using 2 or 3 thick systems. The other interesting thing about this is that we've got a few independent cooling and heating systems here, so we can locally heat and cool, leading to much more efficient approaches. Not unsurprising in an institution like ourselves, there's lots and lots of modelling capability. Virtually everything we do now is modelled with a high degree of confidence. Here you can see just some superplasticity capability and some diffusion bonding. So it's not unsurprising now that we would do mostly modelling before we even think about doing any experiments. Okay, so what I'm really here to do though is to sell you one thing, and that's to sell you the so-called FutureForge. So the FutureForge, and this is just a schematic of it at the moment, is actually a £25 million investment for a new advanced manufacturing facility, the AFRC, launches in 2023. So it's satisfied all its factory acceptance tests, and all about 70% of its site acceptance tests, which we feel that it'll be ready to launch in about middle of next year. It's a truly unique and advanced hot forging platform. In terms of its scale, to start off with, it's a 2,000-ton press for a research institute. That's pretty amazing. And it will help support AFRC's ambitious local businesses, but also international businesses. And I should point out to you that the argument for us is that we need to support even international forging houses who are supplying into the OEMs businesses as well. It's funded by you, the taxpayer. Thank you very much. Okay, it's really three elements. It's been sponsored by the ATI, the Aerospace Technology Institute, Scottish Enterprise, and the High Value Manufacturing Catapult. So they're the three key organisations that have supported the building of the FutureForge. So it's in this bespoke building here. So if you've ever been to the AFRC, the airport, Rolls-Royce in Chinon is here. The airport's about here somewhere. So that's our bespoke area for the FutureForge. It's about 813 metres square. So it's a relatively small building for a really large forge. So the key observation about FutureForge, it's an industry scale forging in a research environment. So a lot of our members are trying to ask the one key question: what size do you have to go to make sure that you're confident that when you do an industrial operation, you can be confident that whatever you did at that scale will reflect at the super large scale, just in general terms. So this FutureForge, we hope, will prove out what scale you need to go to. The other thing that's really important about this particular system, it's trimodal. So it can do open die, closed die, and isothermal forging. So really unique, piece of kit. The other important point about it is fully Industry 4.0. We have 2,000 channels of data that we can capture at any one time during the process, which is fully linked to complete feedback system. So if we had real-time capability of predicting what was happening locally, we could feed back into the FutureForge and actually deliver a response, which would be the ultimate aim of any Industry 4.0 system. And of course, obviously, in terms of the cell, it's about trying to go to net zero, minimise, doing more with less, minimising the amount of forging process you have to do to get the right properties. But from our perspective here and here, the two key observations are we've got trimodal capability, and also if you're going to want to prove out what you need, what data you need in terms of Industry 4.0, this is the ultimate machine to be doing it. So there's no doubt that this is by far the world's most sophisticated research facility in forging and forming by some distance. Here it's being installed. We forgot to put a big hole in it, so we have to put everything through the roof. The standard university thing to do. This is going to be installed. So it's a Shear press. It's a Shear press, but the manipulator is made by Clanton Dynamics, a local company in Scotland, and East Kilbride. And there's some furnaces which are made in Reading. So there's significant UK content still. There's more of it. So there's the manipulator. So the manipulator is here, and you can see it's a really impressive piece of kit. Uniquely, it can do why it looks so sophisticated, apart from the fact that it's fully capable of being automated, is that it can do 100 movements a minute. So it's a pretty fast manipulator. Actually, though, however, it is a great. I suspect I won't be selling it early on about its forging capability. Are we selling most of the time on FutureForge because of these two beasts? What we really unique, worldwide unique, is that we have two furnaces, obviously near industrial scale, that are identical in size, but one is gas-fired and the other one's electric. So for the very first time anywhere in the world, you can make a direct comparison between electric furnaces and gas-fired furnaces in terms of their productivity, issues such as heating up rates, what happens when the door opens, etc., etc. So it's I think this is where I think we're going to start doing lots of experiments even before FutureForge is even opened for business. Lots of companies are very keen to just put in their system, put in their material, and see what happens in terms of heating up rates and the like. We can also, where this is also future-proof, in the sense that we can, this will be converted to hydrogen once we're confident of playing around with different mixes of natural gases and hydrogen. So, just give you a bit of an overview again of what's happening. So the FutureForge facility will feature hot forging platform, including bespoke trimodal industry demonstrators, high accuracy manipulator, 2 industrial size furnaces, Industry 4.0 data capture, connectivity and security. So, we've also thought about all the security issues and the like. And the other important point to note is that particularly for the closed die and the open die, we'll have high temperature die capability. So we can go up to about 600 degrees C for both the closed die and the open die facility process if needed be. Okay, so this is what really wanted to. What does the machine do? What's its capabilities? So here it's a trimodal press, maximum load of 2,000 tons. For the open die, it's 1,200 tons. The closed die and isothermal, it's 2,000 tons capability. In the open die mode, it's a reasonably fast, slowish machine really in some respects. 15 to 92 millimetre second stroke rate. The closed eye, it's around 1 to 25 millimeters a second. And for isothermal, we've got control between 0.04 to 1 millimeters a second. Deliberately, we didn't make the cross-sectional area too large. We didn't want to compete industrially. We didn't want to be doing industrial or commercial activities. So the maximum diameter of billet that we can take is only 0.5 meter in diameter, but it's constrained to be only 1,000 kilograms. So to do the calculations, we're starting off with a very short steel billet if you want. Closed eye, we can only do a maximum diameter of component in the order of 300 millimeters for both isothermal and closed eye. So from a disc perspective, it's too small. So we're not going to be commercially engaged. For the open die, maximum temperature is about 600 degrees. For closed die, we can get up to a die temperature of about 700 degrees. The isothermal, we can guarantee 1200 degrees, but we're obviously going to be working with tool material specialists, and our aim is to get this up to 1300 degrees C eventually. The problem is that materials this size, of this temperature capability, are really expensive. So something else maybe you're familiar with, some high temperature die materials. A good example would be TZM, titanium, zirconium, molybdenum alloys. Our dies would end up, for one process could end up being 60,000 pounds. So they're not cheap. So, you know, these experiments are going to be not cheap. So in many cases, we're going to have to be risk sharing all these processes. And then just showing you, this is actually in the site acceptance test. This was actually some, this was the actual material that we were using during the site acceptance test. This is actually we're just squashing a piece of steel, I think in this case. I don't think we were doing anything special. But as you can see, it heats up nice and uniformly in temperature and does what we asked it to do. So we're very happy. So in fact, of the 3 elements of the FutureForge, we're quite comfortable that the first commercially available type of activities will be an isothermal forging, and followed by the open die, followed by closed die. But by the middle of next year, we'll definitely be running some commercial projects on this particular application. And there's your open die capability, just the same, and just showing you all those activities. But again, it's all been nearly 100% proven out. We've nearly got to the point now where all we have to do is integrate the control system of the manipulator with the Shear control system, and we'll be ready to go. This, I think, is really the important point here. I think in this case here is the 2 furnaces that we have available. We have effectively a gas-fired furnace and electric furnace. The gas-fired furnace has an operational range in the order of 750 to 1200 degrees C, whereas electric furnace has an operational range between 400 and 1250. Between 400 and 650, we've got a fan, so we can actually get fan-assisted heating, so we get a uniform temperature. Above 650, we have to take the fan out because otherwise it'll just melt, and we'll have a slightly different non-uniformity in temperature. But again, that's important in terms of comparing and contrasting the energy transition towards electric furnaces. And not unsurprisingly, we've done a lot of heating modelling. So we've got lots and lots of models about locations of different billets. If you take out one billet and what happens to the cooling cycle if you open up the furnace, what happens to the temperature variation and the like. So we're very comfortable that we've got a really good hold on how we can maximise the efficiency of the heating capability within the furnace. So we're just looking forward to validating that data once the furnace is operating. And the last bit of infrastructure that I want to show you is this. We've got a massive data hub, completely independent real-time data acquisition. 2,000 channels collecting at a very high frequency. So one of the key challenges for us won't be about collecting data, trying to minimise what data we collect such that we don't have to waste loads and loads of information and data storage. So one of the things we're going to be doing first on this system is just trying to work out what's the fidelity of data we need to get accurate models and the like. And this is with this in mind. This is our major strategy. So this is all about developing a true digital twin of forming and forging. Okay, so we've got, this is a, we've done a lot of modelling. We have lots of capability, and the UK has lots and lots of modelling and capability in this area. We want to utilise that. A lot of investment's been made in this area in kind of like pockets. Our job is to put it all together to make a digital ecosystem such that we can also compare with the physical twin, you know, all the data we're going to collect. How does it compare and contrast? And can we use the sensor data to inform the model? So one of the first programs of work we're going to do is literally run a program where we know exactly what the forge has done, and we're going to replicate that in a real model. But this is our aim. What's unique about the AFRC is that we don't really care much about the models. We care of the models, but that's important. But the really important thing for us at this moment is not the actual fidelity of the models. It's the infrastructure that will carry those models, the infrastructure of how those models will integrate with each other, how they will talk with each other, how we'll collect data from other systems, how can external people use it. So we're spending a lot of time developing the infrastructure around a digital twin such that you can use it externally, but also we can set a benchmark for what defines the infrastructure of a metallurgical-based digital twin. Just to give you an example, we actually have got this going pretty early in some areas. This is probably our best example of this. That's residual stress. So about 10 years ago, we started experimentally looking at residual stress at the industrial scale, and we've become really good at it. So we've got a broad range of experimental capabilities to measure residual stress with a high degree of confidence from the nanoscale all the way up to a metre or so in scale. But over those 10 years, we've also developed a significant capability of predicting those residual stresses, both under standard quenching systems, but also in directed types of quenching where we're locally cooling at different rates. So now we're at a situation where we can measure, we can predict, we can validate, but also once we're confident that we can validate, we can even be in a scenario where we can locally cool to make sure we can redistribute the residual stresses, which we have a project to do at this moment in time. But we've got to a scenario now where that may be the residual stress profile, tension, compression, whatever. We're now at a capability now where we can develop, and we have developed, different machining paths to minimise distortion during the machining process. So we're now at a stage now where we've captured enough information, we have enough fidelity in the digital ecosystem and the feedback during that system to locally quench such that we can get the optimum machining path to minimise distortion, therefore reducing the amount of rework in our final customers' parts. Okay, I'm just going to give you a final bit on case study in isothermal forging. So this is just an example. Just a really interesting example for us. So we know that our scenario can only be between 1 millimetre and 0.04 millimetres in terms of speed. If you think about it, if we're going to squash this component here, if we did it at 1 millimetre, it would take around 2 minutes. But if we did it at 0.04 millimetres a second, it would take 45 minutes to forge, much slower. Obviously, 45 minutes is not productive. The problem with 2 minutes, though, is that there's a significant adiabatic heating. Even at 1 millimetre a second, there's still significant adiabatic heating, particularly in super high strength alloys such as nickel powder alloys. So we need to make sure that in this case, we start forging at 1,000 degrees, but we can't go any higher than 1,010 degrees. Otherwise, there'd be some technical problems. So the material should not exceed 1,000, actually 1,010, by the way. The die stress should not exceed 200 megapascals. We really have to keep the stress down on the dies, otherwise we're going to have very low die life. And the maximum forging load, because of our capability in our machine, can't be more than 1,800 tonnes. So what we can do is simulate at 4 different speeds, for example, 1 millimetre a second, 0.5, 0.1 and 0.04 millimetres a second. Obviously you can see that at this point here, at 0.6, the temperature gets above that threshold for certain cooling rates, for deformation rates. So you can see this quite nicely here. at one millimetre a second. You can see that the upper and lower temperature bands exceed that 1110 barrier, whereas if we went really slow, the temperature rise would be much less than 5 degrees C. Okay, so we have a problem. We can't go at this really fast deformation rate because it exceeds that threshold temperature. So what we can do though is do something slightly cooler. So we obviously want productivity, but we can't have adiabatic heating, and also we can't have a stress in the tool of more than 210. But what we can do is we can deform it up for 105 seconds at 1 millimetre a second, so it doesn't reach that temperature. Slow it down, go to 210, go at 0.5 up until 210 seconds, then go down to 0.1 for up until 1,050 seconds, and then the very last bit only go at 0.04 per second. So you can see in this case, this was our baseline at 1 millimetre a second. This was our baseline at the slower ones. But you can see if we went at those conditions, we don't go above that temperature threshold. So just by doing some intelligent modelling, we can maximise the die life, make sure that our material doesn't actually get into any trouble in terms of adiabatic heating. And you can see in this particular case, this is actually the effective stress in the die, and it doesn't go over 200 megapascals either at any point here. And the load doesn't exceed 1,800 tonnes, not even at the very end when we're closing up. So that's what I want to. So I don't want to say any more than that. What I want to say though is the future is FutureForge. And if you have any questions about the FutureForge or the AFRC, very happy to talk about them. But what I'd say is, the AFRC and the FutureForge is really one of those interesting UK investments to try and help the UK forging forming industry actually become competitive from a digital perspective. And if you have any questions, I'm really happy to answer them. And I'd just like to thank all of the sponsors of the FutureForge, which there are a significant number of them. Thank you very much.
Thanks, Brad. That's great. Do you have any questions for Brad? I'll start off. On your open die press forging in FutureForge, are you going to be able to both look at upsetting and drawing, or are you going to stick with side forging?
At this stage, we can, but we're going to have to become very good at utilising the manipulator. So it'll take a while before our guys learn how to control the manipulator. So, but realistically, what we need is some young people who are playing lots of computer games to come and teach us how to actually use the manipulator to do all those things. But it's absolutely feasible, but someone's going to have to learn to become very dexterous at using a manipulator.
Yes. Right.
Yeah, we have lots of examples, Ken, of components that pre-competitive or examples of components, but they're all IP sensitive. So we do lots and lots of work at making components or very close to what the component would look like, but all of them are IP sensitive. So if you went to the AFRC, you'd hardly see anything other than a tube becoming longer, because virtually everything we do has got a certain level of IP sensitivity. So it is a real problem for us that we can't have that many demonstrators. We're going to do a project this year to alleviate that problem, and with a local Sheffield forging house and the flow forming, we're going to make a near-net shaped landing gear component in one go, just to prove the technology out. But if we can make landing gear in the main shafts using flow forming, that will significantly change the landing gear market. So and you can imagine one of our end users is very interested in this. There are lots.
Right.
Yep. So we only have those reheating furnaces. So we don't. So deliberately, if you know, I should point out to you, if we go back to the, deliberately we did this because we didn't want to be anywhere near commercial sensitivity or commercial. So, and the best example of that is the isothermal press. So the isothermal press is just this solid bit in the middle, but if you went to a commercial isothermal press, there would be a preheater on this side and there'd be a cooling system on the other side. We deliberately didn't have the preheater or the cooling system we can, if we wanted to in the future, put them in, but we thought to ourselves, we don't want to be competing with those activities. So all we're trying to do here is prove that a certain alloy can be isothermally forged to a certain shape. What we could do is take that component out, reheat it into another furnace if you wanted to, and do that, but we don't do it. We don't have the capability or the want to start trying to do those things. What we can do though is, and we have done in the past, is once we get to a certain level of technology readiness, we just go to the company and do it on the company. So if the company's then confident about what we've done, let's just do it on their kit, because of course it's their kit that they want to use this system on. Yep.
So economic justification, and is there any sign of an industrial strategy to get that?
Okay, so what I would say is that, and there's two answers to that question. Okay, I mean, the first answer is that the AFRC is a South Yorkshire Forging and Forming Research Centre. It's a west coast of United States Forging and Forming Research Centre. It's an Italian Forming and Forging Research Centre, but it just happens to be based in Chinning. So we're an international research centre that's supporting local industries wherever they are in the UK, but also the large OEMs that are utilising this capability across the world. So that's the answer. That's the first question. In terms of generating local capability in Scotland, so if you obviously are very familiar with the Advanced Manufacturing Park in Sheffield, so the NMIS building, the purple building I was talking about, is the first building on the equivalent Scottish site. So that's the so-called Advanced Manufacturing Innovation District. So, and the aim is to have large OEMs actually manufacturing on that site in the next 10 to 15 years. So there's a significant business case. So for FutureForge, maybe not, but some other, in the very next 5 to 10 years, but some other technology capability that we've been developing in the AFRC, you will soon see that transferred into Scottish manufacturing, with the hope, but probably not from Indigenous investment, but from international investment, which is what I suppose that's all what these parts are all about. So the answer is yes, there's a business case.
All right, thank you. One last question.
So you've talked an awful lot about skills development.
Yes, 100%.
4.0 and 200 data streams coming off.
2000.
2000, sorry. Do you have a plan for data management and that skills development?
Yeah, 100%. So the National Manufacturing of Scotland, a very large element of it is about data management. We have a director of data, effectively, and his job is to, well, in fact, actually, he's teaching. He's already developed courses for the Skills Academy based on on management of data.
Good. I think that's great. As an old steelmaker, we're kind of used to having more data than knowledge, and it's nice to see that you're not going to get into that problem to start with.
I should point out to you though, having large amounts of data doesn't help, because all it will be is, in most cases, at one point. So even if we did 10 experiments on FutureForge, that's a lot of experimental space to touch on 10 points. So it's not about it's about how do I utilize large amounts of data in a sparse network is a real challenge.
Okay, well, thank you very much, Brad. fascinating to hear about these developments. I think it's a great concept to have industrial scale without it being industrially competitive. I think that really helps the industry to use the centre and not to be frightened of it. And a lot of the things that you talked about there chime with what we're trying to do, and I know what a bunch of other forgers in the area are trying to do. So I think it's a great program, and we're really looking forward to seeing results roll out of there. So I'd like everyone to join me in thanking you for a great presentation.